Okay, so we'll continue our discussions. We will start the meeting about the crystal. Yeah, today's meeting we will go to investigate to learn about crystal. Yeah, crystal science. Okay, let me introduce introduction of the material. Okay, I will share my screen. We'll start the class by saying Basmalah. Bismillahirrahmanirrahim. Okay. Okay, we'll share a screen with the sound.
Do you ever think about the research that goes into the stuff that we use every day? Pretty much everything we own contains a complex mix of materials that we have discovered, designed, and then developed. And all this is the result of material science.
Material scientists study the properties of materials and how these properties are determined by the structure of the material and the different components making up the material.
Okay, so even if early humans didn't realize it at the time, we could say that material science started when we learned how to extract metals from rocks and then shape them into tools and weapons and other things that we needed.
The Bronze Age, around 3500 BC, was a major material technology shift, discovering that copper and tin could be combined for the much more superior metal bronze. Following the Bronze Age came the Iron Age, which was probably more important to our lives today. During the Iron Age, the best weapons and tools were made from steel, which is an alloy between iron and carbon. But there was a fine line to get the carbon concentration just right. Not enough, and the steel couldn't be heat treated as much and wouldn't be as strong. Too much carbon, and the steel became hard but brittle.
So as you see, there was some science to get right already then. We just didn't call it material science.
And the tools to make them have changed a bit too.
One of the major steps for material science was the invention of plastics.
The first completely synthetic plastic was called Bakelite. It was presented to the American Chemical Society in 1909 by its inventor Dr. Leo Baekeland. It's not hard to understand why moldable synthetic polymers so quickly became popular when we consider the alternatives we had before them. Ivory, for many reasons a terrible choice of material, used for things like pool balls and buttons. And then the material shellac, which was the substance secreted by the East Asian lac bug. It had to be scraped off of the trees inhabited by the animal before it could be used, for example, to coat electrical cables.
Over the past 100 years, material science has moved forward at an incredible pace, sparked by things like space technology, medical advancements, and of course our love for technology.
One problem that had to be solved before the Apollo space missions was how to get energy. The result was to use the sun, and solar panels were invented. Also, new spacesuits didn't just mean the latest colors, but also improved materials. The new moon boot material later revolutionized running shoes when used as a shock absorbent.
Advancements in medicines also called for new materials.
By applying special coatings to medicines, we can now control where and when medicines are released in the body. And we also have new materials that can be drilled into the bone. And then we have all our electronic toys. Not too long ago, this was what we used for music. And now all we have to do is slide and touch.
Today's material scientists are fighting even bigger challenges, like how can we make sure future generations have the same chance to meet their needs as we do? Here we go. Oh, come on.
How can we keep growing without running out of resources? Materials that won't pollute the environment, lightweight materials to cut energy requirements in transportation, materials that can easily be recycled and put less stress on natural resources.
If you want more specific examples, check out the other videos that we have done on some of the major questions that material scientists here at Chalmers University of Technology are currently working on and trying to find the answer to. That's all for this time. See you soon.
Okay, thank you for the introductions. Chalmers University of Technology. Yeah. So as the modern era, we have to learn about the material. As we know, material was used in our daily life. Material itself has many functions in our life, and the people was seeking for the best material for their purposes. So modern physics will be one of the foundation to be investigated the material. So understanding the material will be helpful for you to understand specifically about the characteristic of material science. Okay, today we will investigate you until at least five topics: material science, semiconductor, XRD, and radiation safety. Okay, so let's look at the slide I have. Yes, material. In introductions. Okay, as you know, previously in 1979, we have a hard disk, 250 megabyte. But look at the size. The size will be very big, right? The huge. So it's not easy to carry. And also the advancement of technology relating to its memory device will be still limited. But now the device was transformed into another shape. It will be denser and then lighter. So if previously we have 250 megabyte with its size, but now we can carry 64 gigabyte, and also in the future we can get 1 terabyte into one what small device like micro SD. So it will be, understanding the material will be so important for our new era. Look at the first hard drive, 2.52 gigabyte. Look at this, the weight is 250 kilogram. How heavy is it? Wow, it's very heavy, right? So it can be carried by everybody. And also the advancement of the material will transform the new technology. As we know, the new technology era now, we have in the giga era or terabyte era. So in the future, you will see the material will be heavier, denser, and then lighter, and it has a good capacity, faster, right? So you will find the computer is very fast. So that with the very fast processor, so we can develop new technology, new media. Okay, so how do you know? I have view that your understanding of the material will be important. So that's should be excluded in IPSC curriculum previously, but now I would like to engage it into this content. So look, the first investigations. Could you interpret what is the meaning of the graph? Look at, I have three graph. 1, 2, 3. How can you interpret from the graph? Look at, when you investigate the graph, you have to investigate 2 parameters here. What is it?
Temperature in Kelvin.
Okay, so what does it mean?
So it meant that if for the metal, the larger the temperature is gonna be, the larger the electrical resistivity.
Yes, so what does it mean? The electrical resistivity will increase as the increase of temperature. So in order to achieve the material having a low electrical resistivity or high electrical conductivity, what should you do?
It has to be in low temperature.
Okay, very good. Okay, next, look at for the insulator. In the insulator, as the increase of the temperature, it decreases negative exponential, of the electrical resistivity. But now the value, it's not approached to 0, means that the characteristic still insulator. And look at superconductor. Have you ever heard superconductor? Look at this is the properties of superconductor. Superconductor at the low temperature. Look at, as you know, 0 degrees Celsius refer to 200 what? 73 Kelvin. Yeah. So look, imagine here in 50 Kelvin. Yeah. Okay. Less than we call it as a Debye temperature. Debye. So look at the resistance becoming 0. So that we call it as superconductor. What is the consequence of material with the superconductor properties? It could carry a large current. Yeah, current can be carried by the material having a superconductor properties. So as consequence, with the large current, it will create a large magnetic field. A large magnetic field can carry a people through maglev, magnetic levitation train. Yeah, carry people in a super fast speed. Okay. So look here, if we look the origin of the material, everything is just about the carbon. Everything is carbon, but the carbon, when it has a different crystal, look at, for example, graphite, it was a metal. Diamond, it was insulator. But bulk minister fullerene, it is superconductor. So the same material made of carbon, when it form into a different crystal, it will have another electrical properties. It means that the way to make the crystal, so it will be so important in material engineering. Yeah, that's my field. Okay, so what will you learn? So we'll learn about this material. So as we know, in the universe, there are space and energy. As we know, in the energy itself, in the certain condition, energy could create the particle. So as how the gods say, kun fayakun, with the huge energy, God will be easy to create the material. So material created by saying kun fayakun, the large energy from the God. So God could create the material. So firstly, initiated by Big Bang theory. So energy from our God, realized into particle. And also the same thing, particle could disappear to be energy. So we call it as the nuclear energy, right? Have you ever learned before? Nuclear means that the energy sometimes is not only converted into another energy, but energy could disappear. Energy could disappear into material, or material could disappear into the energy. So we call it E equal to mc squared. So we consider the way is mass defect. Mass defect. E equal to delta mc squared. So as proposed by the Einstein. Okay, so that's reflect to modern physics, right? Inside the nuclear atom. Okay, so inside the particle, we consider atomic and non-atomic, and also the state of the material of composed of atomic. There are gas, solid, and liquid. But also, according to its structures, the material are amorphous, quasi-crystal, and then crystal. What's different? Okay, we will learn it later. So this is the scope of, we call it as the material science. Yeah, if you are interested in the material science, you can continue to a master degree in material science engineering in another university. Okay, so inside the atomic, we consider, the scope are metal, semi-metal, semiconductor, insulator. Wow. Okay. And then the atomic, that are gas, solid, liquid, and so on. Here, so they show the material zone. So in the material itself, we have crystalline, yeah, amorphous, and so on. So I have a video. Maybe this video could help you to understand deeper about the crystal. Okay, so here. But I will jump for some point. Oh, crystal. Wow, that's...
Welcome back! Today's video will be about crystals. What they are, how they are formed, how they work on the energetic levels, and meanings of some well-known crystals. Let's start with how crystals actually work. First of all, it's important to realize that our entire body system is just energy that shows up in different densities and patterns. Our thoughts and emotions are connected to our physical bodies and have a density of their own. When these patterns of energy work in a balanced way, then we experience our health. However, these energy patterns can be disrupted, which then results in poor health, from headaches to serious diseases. Crystals are thought to be the most stable form of matter in the universe due to how they are formed within our planet. Crystals grow in the Earth's crust over millions of years at high pressures and heat, making them objects with the most energy, as each step in the formation of a crystal contains energy. The crystal's journey begins deep below the planet's surface, where lava and hot fluids circulate. Crystallization occurs when layers of the planet's mantle fracture, which allows heated gases and liquids forced by high pressure rise towards the surface. Elements such as water, oxygen, sodium, iron, potassium, and magnesium are also present, and in the process they merge and dissolve, with other elements being pushed to the surface. As this mixture rises and passes through cooler, less active layers of rock, crystals begin to grow in the rock's cavities and crevices. Crystals will form depending on the specific environmental conditions and the mixture of the elements that I mentioned. Growth, shape, color, hardness, and size depends on the temperature, water, light, pressure, time, and space. Crystals are alive like everything else in the universe. They work with the human energy field and are able to diffuse, absorb, move, or shift energy within the body. Crystals vibrate at different levels depending on their composition and color, as do the cells in the human body. They all vibrate on their own frequency, as do the energy centers in our body, our chakras. A video about chakras will be linked in the description. Crystals operate by naturally focusing and magnifying the body's innate energies, dissolving and equalizing emotional, mental, and physical stress. They can alleviate suppressed or unreleased pain and help to make desired shifts in every aspect of one's being. So when we come into contact with a crystal, its vibration interacts with the vibration of our cells in our human body. First of all, yeah, it's not a myth that crystals have energy. Crystals actually have a very high and precise rate of vibration and are utilized in modern technology. This includes liquid crystals in calculators and clocks. They're also used in credit cards, phone lines, and lasers for microscopic surgery. Working with crystal energy helps the body to find its natural rhythm and restore its energetical balance. Crystal healing is basically laying of the stones of different vibrational frequencies on your body in order to effect healing or change. It may also involve this. They just knew so much about themselves, nature, and everything, the universe. It's just as if we somehow lost that knowledge. I don't know. The ancient Egyptians used crystals for protection and health, and they even buried people with a piece of quartz on their forehead to help them guide them into the afterlife. Dancers wore ruby stones in their belly buttons to enhance their sexuality, and wearing a necklace over your heart was also intended to bring love into one's life. Forehead crowns were also worn to stimulate the third eye. Pharaohs carried zinc cylinder and a copper cylinder, both filled with quartz to balance their ka and ba energies, the equivalent of yin and yang today. Quartz crystal spheres in ancient Japan were thought to represent the hearts of dragons, which symbolized wisdom and power. Ancient Greeks rubbed themselves with crushed hematite before going into battle, thinking that it would make them invincible. Amongst the Romans, crystals were used in medical treatment and to attract desirable things, protect in a battle, and enhance health. In India, the sacred 5,000-year-old religious texts discuss the use of crystals in different diseases, mental illnesses, and conditions, as well as specific.
Okay. So she has discussed about the crystal, the origin of the crystal from the nature, and also some another society. Yeah, crystal in the society, as we know, crystal used for mental health and then therapy and so on. But now the people also use the crystal, especially for the technology. So crystal will be so important in our daily life. Okay, so I have also another video here. So it will relate to the material of the crystal and the characteristic of the crystal.
Deep beneath the geysers and hot springs of Yellowstone caldera lies a magma chamber, produced by a hotspot in the Earth's mantle. As the magma moves towards the Earth's surface, it crystallizes to form young, hot, igneous rocks. The heat from these rocks drives groundwater towards the surface. As the water cools, ions precipitate out as mineral crystals, including quartz crystals from silicon and oxygen, feldspar from potassium, aluminum, silicon, and oxygen, galena from lead and sulfur. Many of these crystals have signature shapes. Take this cascade of pointed quartz or this pile of galena cubes. But what causes them to grow into these shapes again and again? Part of the answer lies in their atoms. Every crystal's atoms are arranged in a highly organized, repeating pattern. This pattern is the defining feature of a crystal and isn't restricted to minerals. Sand, ice, sugar, chocolate, ceramics, metals, DNA, and even some liquids have crystalline structures. Each crystalline material's atomic arrangement falls into one of 6 different families: cubic, tetragonal, orthorhombic, monoclinic, triclinic, and hexagonal. Given the appropriate conditions, crystals will grow into geometric shapes that reflect the arrangement of their atoms. Take galena, which has a cubic structure composed of lead and sulfur atoms. The relatively large lead atoms are arranged in a 3-dimensional grid 90 degrees from one another, while the relatively small sulfur atoms fit neatly between them. As the crystal grows, locations like these attract sulfur atoms, while lead will tend to bond to these places. Eventually, they will complete the grid of bonded atoms. This means the 90-degree grid pattern of galena's crystalline structure is reflected in the visible shape of the crystal. Quartz, meanwhile, has a hexagonal crystalline structure. This means that on one plane, its atoms are arranged in hexagons. In 3 dimensions, these hexagons are composed of many interlocking pyramids made up of 1 silicon atom and 4 oxygen atoms. So the signature shape of a quartz crystal is a 6-sided column with pointed tips. Depending on environmental conditions, most crystals have the potential to form multiple geometric shapes. For example, diamonds, which form deep in the Earth's mantle, have a cubic crystalline structure and can grow into either cubes or octahedrons. Which shape a particular diamond grows into depends on the conditions where it grows, including pressure, temperature, and chemical environment. While we can't directly observe growth conditions in the mantle, laboratory experiments have shown some evidence that diamonds tend to grow into cubes at lower temperatures and octahedrons at higher temperatures. Trace amounts of water, silicon, germanium, or magnesium might also influence a diamond's shape. And diamonds never naturally grow into the shapes found in jewelry. Those diamonds have been cut to showcase sparkle and clarity. Environmental conditions can also influence whether crystals form at all. Glass is made of melted quartz sand, but it isn't crystalline. That's because glass cools relatively quickly, and the atoms do not have time to arrange themselves into the ordered structure of a quartz crystal. Instead, the random arrangement of the atoms in the melted glass is locked in upon cooling. Many crystals don't form geometric shapes because they grow in extremely close quarters with other crystals. Rocks like granite are full of crystals, but none have recognizable shapes. As magma cools and solidifies, many minerals within it crystallize at the same time and quickly run out of space. And certain crystals, like turquoise, don't grow into any discernible geometric shape in most environmental conditions, even given adequate space. Every crystal's atomic structure has unique properties, and while these properties may not have any bearing on human emotional needs, they do have powerful applications in materials science and medicine. Have you ever wondered why you can see through glass, or what fire is made of? Did you know gold doesn't originally come from our planet?
Okay, we welcome from you. After watching this video, what can you conclude from the description above?
May I try, Doctor?
Okay, Rizky, please.
Okay, so sorry, it's just my opinion. I don't know it is right or wrong, but from the first video, I think the crystal have the large energy. So because, for example, when the magma on the earth crunch and what kayak mengeluarkan magmanya and the ions is precipitate and make some what precipitates to become crystal, and so every atoms have different arrangements, so that's why the shape of the crystal is not same. Yeah, so it depends on atoms arrangement, temperature, and also pressure, and also density. And then for the diamond is crystal that we can find on the deep deep in earth layer. So di dalam lapisan bumi yang tercipta karena ada dari patahan gitu, dan then the ions is precipitate make the diamond crystal, and the arrangement of the diamond is like solder column. So that's why the light can pass through diamond and then we can see the light like sparkle or shining in the diamond crystal, sir. I think that's my opinion. Correct me if I'm wrong. Thank you.
Okay, thank you very much, Rizky, for what you have watched. And also another opinion, still welcome from one student. Arni, Arni, are you there?
Yes, sir.
Okay, so what can you conclude from what you watch?
Is crystal from the we don't from the earth, and sir boleh mix gak?
Yeah, okay, try what you can for your best.
Yeah, so crystal make from the jadi dari pembuatan yang di bawah apa ya, kayak panas bumi gitu. Terus dia juga terbentuknya dari unsur-unsur yang kayak Si gitu maksud tadi tuh.
Silicon.
Ya. And pokoknya terbentuknya sempurna gitu, sir.
And then what next?
Crystal formed from large energy, from, for example, the magma on the earth release some ions. And the ions precipitate to make crystal. The shape of the crystal itself depends on atoms arrangement, density, pressure, temperature. This is it, sir.
Okay, and how fast the precipitation happen? Yeah, it will indicate the crystal will be, the atom will arrange as amorphous, as discussed it inside the quartz glass. Yeah, you have ever seen before? Yeah, when the glass precipitate, yeah, cool, very fast. So there is no time for atom to get a self arrangement. Yeah, so the glass will form as amorphous. But another material like carbon in the high pressure, and then its pressure is so low, so when it released to the earth, so it will create a crystal, hexagonal crystal. Okay, so it's not only solid, but also liquid could also form a crystal, so call it a liquid crystal. Yeah, and we know here liquid crystal display, right? LCD. LCD. You can just touch LCD and you will feel like a wave, like a water. You touch water and creating a wave. So because it made of polymer, this polymer behave like a liquid base. So because it's liquid crystal display. Yeah. And you also touch your LCD in your phone. So it also apply liquid crystal display. So why we can arrange or create a good electrical behavior in LCD, because in the crystal itself, the atom was formed well, yeah, so that we can make it line X and Y and interpret it as axis, yeah, X and Y. Well, you contact, yeah, so we apply the electrical or electrical field apply into the display, so the display will respond, yeah, your actions to the LCD. Okay, another here. So in the crystal also there are metals, ceramic or glasses, or polymers. Yeah, have you ever know what's different? Plastic, is it polymer, ceramic, or metals? Plastic?
It's polymers.
Polymer. And then what else? Would you please give one example of ceramic? Why do people create the ceramic?
Because It's absorbing heat, I guess.
It can absorb a large number of heat. When we made the space aircraft, so we need to protect the passenger inside from the high temperature. So the people design the ceramic. Okay. Well, metal. So what is the main function of the metal? It was shiny. It's not different. It is different from ceramic. So metal is shiny, and that it has a good electrical conductivity. For the metal, right? Okay. And also, what else? Does it elastic?
No,
Yes.
it's rigid.
Metal rigid.
Metal.
Rigid, doctor.
Rigid. Elastic. It's different from here. Elastic means when we give a treatment or a force, to this material, so material will return back into its origin position. So metal, is it elastic or not?
Well,
So
but we
just
are
touch.
it's a spring. It's elastic.
Spring is elastic, so
Yes.
metal is elastic. Metal is elastic. Because when you give a force to the metal, so metal will come into the origin position. Okay. So continue. Material, there are all of composite, sandwich, lattice, segment, and also we now we call it alloy. What is it? What is alloy? Alloy?
Is it it's made of from a lot of metals.
So the mixtures of the metal will form alloy. Okay. So how do you create the alloy? So could you do the experiment to create an alloy?
I've never done that.
You have never. So we have
But I think it's about melting some metals together.
Yes. So we have to treat it in the high temperatures. So to form an alloy, we have to mix it in high temperature. We need the equipment, we call it furnace. Furnace. Furnace is the equipment to give a specific heat, so that it can be melted in high temperatures. And afterward, alloy will form. With a certain characteristic we expect. Okay, so ceramic, and then another example, amorphous, and then the crystal, and then the metal, and then polymer and graphite. So this is the functional material we have. And also another characteristic of material we know, conductor, semiconductor, and insulator. So could you differentiate it? What's different between conductor, semiconductor, and insulator?
Conductors can conduct the electricity well, while insulator cannot conduct electricity well. And then semiconductors is between both of them. It can conduct electricity, but at certain condition, it cannot conduct electricity.
Which condition it can conduct the electricity?
Maybe where we give it some heat, or
when we give a heat, it can
by heating the material.
It. So if we hit it, will it perform, or it could carry electricity if we increase the heat, increase the temperature of the material? You have to increase it or decrease?
We have to increase the heat.
It's vice versa. You have to decrease the temperature so that semiconductor could behave as conductor. Another way to make semiconductor to carry the electricity, how should you do? I have a semiconductor and I want to produce an electricity from this material. So what you have to do? Okay, we have two ways. First, give high potential. Give high potential difference so that semiconductor will carry an electricity. Yeah, in high potential difference, semiconductor will behave as conductor. Yeah, okay. And what else? Give a light energy. Yeah, if semiconductor receive a light energy, so semiconductor will produce an electricity. So we apply it as, what you call it? Solar cell. Yeah, solar cell is the material which can carry, yeah, a current because we give an energy to the material. Yeah, so semiconductor now will be very fundamental. Yeah, so it will be very what without a semiconductor, yeah, we will not have a computer. Yeah, without semiconductor, we cannot receive an electricity because electricity could receive from the sun. Yeah, without the semiconductor, there is no handphone. Yeah, without semiconductor, there will no calculator. So semiconductor will be so important for us because semiconductor can behave a logic gate. Do you remember logic gate from integrated circuit? Electricity and magnetism. Okay, so in the logic gate, yeah, it apply logic 0 or 1. Yeah, depend on you apply the potential difference across the probe. Okay. Yeah. So now this is the scope of material science and engineering, physical, mechanical, and also it will be very crucial for to try corrosions, or casting, welding, powder metallurgy, machine. Yeah, wow, it will be very attractive. Yeah, it's apply science, right? Apply science. So it will be directly applied to the daily life. Yeah, the people working on material in our era. Okay, so we have here crystal, atomic. Yeah, so if last week you have learned about what the properties of atom, yeah, but now when atom form, yeah, into a crystal, so the crystal will have a specific characteristic. Crystal has electrical properties, crystal has chemical properties, crystal has mechanical properties, crystal has optical properties, yeah, and crystal has acoustic properties, acoustic, because music instrument, it's made of material, right? So what make it different? Harpa, yeah, and then a violin, and then piano, yeah, and then suling, yeah. So it made of a different material. You will hear it, the sound, it sounds different, right? When you listen a different music instrument, well, it show the same frequency. Yeah. So material will provide the different acoustic properties and wave properties. So can you explain wave? Yeah, wave in terms of acoustic, and then optical properties. Maybe it is what it can reflect the light, it can transmit the light, it could absorb the light. Yeah, so the crystal will have a specific properties, and then mechanical properties. So would you please explain the example of mechanical properties of the material? It was very strange. And then
May I try?
Okay, Rizky.
So for example, chemical properties of sugar, it is hydrogen.
Mm-hmm.
Wait. hydrogen, carbon, and oxygen. So in several ways that, for example, photosynthesis ways that can produce the sugar as the matter.
Okay, thank you. Okay, so this is, I think the slides should be over here. So another scope, okay, I think should be enough. Okay, we will continue to another discussion. So here, amorphous. Okay, I have another slide. Okay. Is there any questions? So before we continue. If you pray, salat asar.
Dancer.
Okay, yeah, okay, thank you. Okay, now we continue here. Solid state physics, yeah, material. Into material. So we continue here. Crystal, yeah. So crystal structures, as we know, there are the specific properties, gases, and then liquid, and then solid, yeah, depend on the density of atom, yeah, okay, placed on the side, yeah, or we call it lattice, yeah, lattice. Okay, gases, the atomic, it's too far away, so any atom will be easy to move. And also liquid will have van der Waal force. Or solid, we have crystal, yeah, okay, it form crystal. And crystal itself, we have three types: single crystalline, polycrystalline, and amorphous, yeah. Okay, single crystal means it made of one shape of the crystal. Polycrystalline, there are many crystal inside the material. And then amorphous, it's not crystal. Okay, single crystal, yeah, it's a periodic atomic structures occurs in its whole volume. Yeah, so it made of single crystal form here. It will be symmetry. Yeah, each atom vary other equivalent atom in the structures. Yeah, the size. Here, this is the fact. Yeah, this is we rarely find the single crystal in the nature, because in nature we will find the material having a polycrystalline. So when we are seeing, yeah, the atom through scanning electron microscope, yeah, you will see the grain boundaries. Maybe if I have video, maybe it will be interesting if I can show here. Viewing grain in scanning. I want to try to search the video first. So which one maybe it will be? Here, maybe I can skip from one part to another part.
My name is Charles Zona, and I would like to welcome everyone to today's Macron Group webinar. That these bright materials that are laying there on the surface are actually particulates that are crystalline materials, and they're quite birefringent. So there's a lot of things that we can see with these types of illuminations that'll help us.
Maybe
can be used then for other imaging manipulations with software and so forth, if you're trying to do some quantitative work with that. So I'm going to finish up a little bit here to give you 4 different images of the same region, same field of view, using each of these 4 techniques to show you what they can really tell you.
Okay, maybe I can see
Here's
it
a
from
polished
another
brass.
example, maybe here. Here. Look at, it was a grain. Yeah, in the real activity, we do it in the lab. Oh, here, maybe you can see. Yeah, it show a different grain. Yeah, any grain has a different crystal. So this is another example. So, sir, could you predict, for example, Mufti, if you are viewing this picture, what can you analyze?
I can't analyze anything because I don't know what is it.
So I just see here a grain, yeah, buletan. But the first, what can you investigate? This is about uniformity of the grain is 1 point. Yeah, does the grain having a same size? Okay, the uniformity of the grain. Secondly, could you predict? Look at, this is another example. The size of the grain. Yeah, grain have a different size. As we know, for example, do you know memory? Yeah, a chip, yeah, memory. For example, 64 gigabyte. What's different from memory having 1 terabyte? What make it different?
The structure, sir.
Not only the structures, but also the size of the crystal.
The size.
So if we have smaller size of the crystal, as we know, 1 crystal will save 1 magnetic field. Yeah, a summit like that. So that a crystal having the smaller grain will have a large amount of data could be stored on the material. Yeah. Okay. So what make it different? CD, DVD, Blu-ray, you know? Yeah. So look at CD and then DVD, crystal structure. Maybe if it was available, we can investigate it more. So what make it different? Because of the size of the grain, the crystal inside. So that the size of the crystal will have a different physical properties. It's not only chemical properties. If the people can engineer, yeah, okay, the activity, yeah, to perform the chemical reactions in the laboratory, so that it can create the crystal having the smaller grain, yeah, so the people could create storage having a larger capacity. So this is what you mean. Understanding the crystal will be so important. Yeah, so we just engage you. Are you interested or not? Sir, it's to what it's too deep. But just the way of here is the modern physics era, modern science era. So the people investigate. You know quantum dot. You know quantum dot. Quantum dot. Quantum dot is a material with the same chemical properties. For example, this one. Look at quantum dot. It made of the same atom, but it show a different color. Why? Could you give me the reason? Here, this one is the example of the quantum dot. Look at it, show a different color. What make it different? It made of the same material. Yeah, CDSE. Yeah, you know, cadmium selenide. Yeah, or silver nanoparticle. But it glow in a different light, different color. What make it different? Look at here. This is the reason behind. Because the size of the crystal is different. Look at when the size crystal bigger, yeah. So when there is a particle or a photon, yeah, penetrate to the crystal, it emit the light in a different wavelength. As we know, wavelength is the vibration, right? Due to the vibration of the atom. When we have atom with the larger size, yeah, so atom will vibrate it weaker. When we have a smaller atom, let's compare the size. For example, is there any example? Me and Mufti. Mufti is bigger than me. This is an example. I receive the same energy, yeah, Mufti and me, but I vibrate it faster because I'm lighter. Because I vibrate it faster, yeah, I have a greater frequency. Yeah, my frequency is greater than Mufti. So I emit blue light while Mufti emit green light. So look at that's modern physics era. The size of the particle will influence of the fluorescence. Fluorescence. Yeah. So could you receive my mind? Okay, so we are not studying the formula. We are studying the real natural phenomenon. Yeah, you can go into the deeper insight into the formula, but it will be make you stressful, right? Should be interesting if we discuss the phenomena rather than investigating the formula of what F equal to ma and so on. Okay, so could we continue to another discussion, or do you still have any questions? Look at the size of the grain will indicate a different storage of memory. Yeah, the different size of a crystal will make a different wavelength of quantum dot. Yeah, and then different size of the crystal will create a different efficiency of the solar cell. So it will be interesting. And also different size of the particle, or here, look at lead, you know, lead, yeah, material, lead material. For example, look at this one, lead, right? But it show a different color. What make it different? Because it made of the same material, but having a different size. So lead will emit a different color. For example, look at, we show, we merge, in the laboratory, okay, combine alloying aluminum, gallium, and arsenide. Yeah, it can emit red light. Red light, look at, yeah. So we investigate something what deeper than previously. If lead connecting to positive and negative, it glow, but now we want to ask why lead could glow it red color or blue color or green color. It's due to the emission of photon. Okay, so maybe I will continue to another PowerPoint. We still have another PowerPoint here. Yeah, this one polycrystalline. And then amorphous. Yeah, we know it. Made of a randomly oriented atom, ion, molecule that do not form divine pattern or lattice structures. So call it amorphous. So the science studying crystal, we call it crystallography. Yeah. So crystallography. Okay. For example, you meet with the seller. Okay. He sell ring. Yeah. Gold ring to your mom. Yeah. How do you make sure the presence of the gold in the ring? Because the gold, sell by the marker in the market. Yeah, we have a different range of price, right? Agnia, you know it, or Dea, Atoila, or Arni, yeah. Who want to get married soon? So you have to buy a ring, at least a ring, from copper. So that's why Rasulullah say, at least you have a ring from iron or copper, you can give it, to your prospective wife. So how to identify the quality of the ring? So we need the crystallography. So crystallography is the science to investigate, to study about the crystal. Okay, so inside the crystallography, we investigate how atom form into a crystal. If previously in chemistry, we just combine, oh, this is sodium chloride plus what else, and result, what else, yeah. But now this is, we investigate a metal, especially in metal, yeah. In big group, right? Big group. In chemistry, you commonly studying a group, right? From group 1 to 1A to A or 3A. But in physics, we study in the group B. Yeah, 3B, 5B, 4B, okay? Something, the reason behind the magnetic field, something behind the ferromagnetic material, something behind paramagnetic material. Wow. Is it physics? Yes. Okay, yeah. So when atom form, yeah, it create a good uniformity. We call it lattice. Lattice, yeah. Lattice is a place of the atom. Yeah, when it order it neatly. Yeah. Okay, in certain positions. In lattice itself, when a lattice, we connect it into the basis. So we call it as a crystal structures. Crystal structures, we have, for example, face center cubic, base center cubic, orthorhombic. So this is what the name of crystal structures. There are anates, there are brookite, there are castrite, there are chalcopyrite. Wow, oh, it's many things you can learn it. I feel that it is the first time you listen this term. Okay, yeah. So this is an example. I have a lattice, an atom, yeah, form uniformly and connect it into the basis. So we call it as crystal. Another formation of the atom could be rectangular in a 2-dimension, square, hexagonal, center rectangular. Okay, so this is the term. What make it different? Depend on here, the length. Look at, if the length of A and B similar, so it was square. If the length of B longer than A, it is rectangular. And also consider the angle between A and B. Look at the angle. This is 90 degree. Yeah, hexagonal. Although I have A and B the same, but the angle of AB is 60 degree, so it will be hexagonal. Or AB is similar, but the angle between A and B is approach 90 degree, so we call it square. Yeah, so this is the unit cell. Yeah, we know this is composed of one atom, and one atom form connect to another atom, connect to another atom, yeah, into metallic bonding. Do you remember? Metallic bonding. We are ionic bonding, you know, hydrogen bonding, covalent bonding. Yeah, in physics we call it metallic bonding. Metallic bonding happen when we give a heat, yeah, into the material in the high temperatures, and it decrease, it freeze, yeah, by the time it form, yeah, uniformly, so it will create a crystal. So this is an example of crystal in the 2 dimensions. Yeah, the small amount of here, this one, we call it as unit cell. Okay, could you confirm what is unit cell? The smallest arrangement of the atom. Yeah, when it copy, yeah, to right side or to left side. Yeah. Okay, here, so it will be crystal. Okay, and also here we have a barrier. Afterward, we call it grain. Okay, grain. So what Dalton say? When you are cutting a material into the smallest part, you will not found atom. You will found grain. But to know. Any question, please? Okay, so how the people study an atom? This is an interesting discussion. You know, a chemical Nobel, yeah, chemical engineer Nobel here. He or they create mobile robot made of atom, could be controlled by electricity, and it can penetrate to your brain here. So you eat, yeah. What the name? A drug, and then the drug could be controlled, yeah, by outer machine using electric field, and then this drug could carry something into your brain. Mobile motor chemistry. He got a Nobel making a robot, but it's chemical robot that's very small because the size is nanometer. Smallest robot in the world. Mobile robot, but I have to fix the paper. But he got mobile motor, chemical motor molecule. Maybe I have to fix the here. Is there in a video? Maybe the video high performance molecular motor with minimal design. Look at molecular motor protein. Maybe it work. Maybe try to open. How the people now modern era so create molecular motor. Wow. Is there any video to show you? Forget. Nobel. Here. Molecular size motor get the chemistry Nobel. Okay. Can I see his invention? Maybe it work. Here, chemical Nobel. Okay, so but is there any visualizations? But here, it's look like a tire. Yeah, this one like a tire, and then here's like a tire. It could be controlled by outside magnetic field, so it can rotate. Set like a car. Wow, in small size. So it will be unit cell, and finally get a 3-dimension. So in the 3-dimension part, we have some term. First, simple cubic. Look at this is the arrangement. Simple cubic. This one, body center cubic, means we have a body atom located at the center of the body. Yeah. This one, face center cubic, means this is here. The same thing, face to us. It's located the same case as A, location A, B, and C. This is in parallel. Face center cubic. Here, not inside, but it face us. Yeah, so it located here, not in the center, but it was in the surface. Yeah, could you imagine? But this is in the center between this part here. This is base center cubic. Here it was face center cubic. Yeah, and here without any atom, yeah, inserted, we call it simple cubic. Because we know crystal means the lowest energy of atom form. Yeah. Okay. So this one is unit cell. We have also another term, cubic system, and then hexagonal, triclinic, monoclinic, orthorhombic. Wow, it's very complicated. But if you are interested, you can download the video from YouTube by yourself. Yeah, you can further study it by yourself. This is the example we have. Cubic, yeah, face center cubic. This one, what we call it? Base center cubic. Yeah, here face center cubic. Yeah, this one tetragonal. Here also tetragonal, but base tetragonal. Face center cubic. Yeah. Okay. Here side center. This one side center. Look at side center, face center, body center. Orthorhombic, hexagonal, monoclinic, triclinic. Wow, that's will be, yeah, if you are interested in the detail discussion, you can perform it directly in the lab to prove the evidence. Okay, this is an example. We have sodium chloride. Wow, sodium chloride is one of the perfect example of what here is the structures. Simple cubic, look at simple cubic lattice. Okay. Okay. So that's why sodium chloride could create a crystal. Here is the crystal, or another crystal you have found from sugar. Because it show what located it uniformly, so it show optical properties. So light will easy to pass between the atom. Yeah. Could you imagine? Because look at when it form it, yeah, place it form uniformly. When there are light here, light can pass through the material. So this material can transmit the light. It has a good optical characteristic. Okay, and also we know, yeah, in the crystal there are many interactions. Why it can form a crystal? This is one example. This is the reason. Because the reason there are ionic bond, covalent bond, connected to chemistry, metallic bonding, van der Waals, and hydrogen bonding. For example, is ionic, yeah, just to overview, yeah. Okay. Covalent, yeah, no need to me to detail discuss, right? Because you have learned from Bu Rika or Bu Eli. Okay. Okay. Ionic here, metallic bonding. Yeah, this is metallic bonding means it could facilitate the electron to transfer to its orbital. Do you remember orbital? Yeah. Conduction band. Yeah, and valence band. Yeah, so in ionic bonding, so all electron will be easy to transfer it through conduction band. Yeah. Van der Waals bonding, yeah, that's one of. You know how the people design the material to prevent van der Waals bonding? You know, super hydrophobic material. Maybe I can search here. Have you ever heard super hydrophobic material?
No, sir.
Okay,
No.
so I will show it to you. Super hydrophobic material. You will see its functions because the material, its function will be applied to another applications. You know, kayak air di daun talas. Here, super hydrophobic. So you can create, yeah, like a leaf, daun talas. Yeah. Okay, so look at. So the crystal must be designed so that it has its unique characteristic, super hydrophobic. Can you listen the voice?
Yes, sir.
Yes, sir.
Okay. Look at it floats. Whoa. What is function here? Super hydrophobic for a car. Without cleaning it, the car will always clean because there is no dust and water will attach to the surface.
Welcome back to Detail Garage. Today we're going to show you how to apply Carbon Flex C9 to give a brilliant shine with durable protection to any painted glass or wheel surface. Now, Carbon Flex C9 is the world's most advanced protective coating. It's going to give a durable 36 months of protection with a brilliant hard candy shine to any color vehicle. Now, it's designed to work on clear coat and conventional single-stage paintwork, and it's going to give the most durable protection that any product can supply on the market. Now, this uses advanced carbon technology that bonds to the paintwork and creates an artificial protective layer, which resists all type of contaminants and defects. So it resists things like water spots, stains, and even helps resist swirl marks and scratches from normal washing or taking it to the car wash. Now, Carbon Flex C9 is easy to apply, and it works on all painted, glass, and wheel surfaces. It's going to give a durable protection and a brilliant hard candy shine. Now, to apply it today, we're going to be using a few things. We're going to be using some premium edgeless microfiber towels. We're also going to be using the Durafoam coating applicator block and the Chemical Guys Optical Select Micro Suede Coating Applicator Towels. Now, all these things are going to do a great job of applying Carbon Flex C9 and giving the highest end results possible. Now, to demonstrate the protective qualities and the brilliant shine of Carbon Flex C9, we're going to use some painter's tape. We're going to place it right down the middle of the hood to show you a complete 50-50 difference. So now let's start with the application of the Carbon Flex C9. Now, the first thing you want to do is wash the entire vehicle. So you can either do a waterless wash, a pressure wash, or any type of foam gun or foam cannon. You want to make sure that the whole entire surface is completely clean. Now, you also want to follow up with a clay bar treatment to remove any contamination or any above surface contaminants that are stuck on the paint. Things like overspray, tree sap, rail dust, industrial fallout, all these things will interfere with the actual coating adapting to the paintwork. So you want to go ahead and make sure that you remove all the dirt and debris before you start applying the coating to your vehicle. Now, if possible, you want to make sure that the paint has 0 defects. So go ahead and give it a good polish with a machine polisher, either a rotary, dual action, or by hand to restore the paintwork and ensure that there's no scratches on the surface. Now, any scratches that are on the surface that are applied underneath C9 Carbon Flex are going to be there for 36 months. So you want to make sure that no scratches are underneath the coating before you apply. Now let's take our Optical Select Micro Suede towel and our Durafoam coating applicator block, and we're going to place them together. Now you want to go ahead and wrap the Micro Suede applicator towel around the coating applicator block to give an even, smooth application. Now you want to make sure that you use micro suede towels or applicator towels to give a durable, clean finish with no streaks when applying the Carbon Flex. Straight lines and go the other direction. Full application, 20 minutes, and we're going to buff off any remaining Carbon Flex C9. Now we're going to use a premium black edgeless microfiber towel to buff off the residue. Now if you have to, any residue that really stand wheel surfaces. Now the best thing about this coating is the surface, and we're going to resist every.
Wow, I need the test. Yeah, that's not only to coating. We need the test also. Okay, so as we see another taste from super hydrophobic here. Okay, so what makes a car different when we apply the super hydrophobic into the car? No need the wiper. Yeah, no need the wiper. A car, because all the water will directly rolling down. So that's an example of super hydrophobic. No need to you to clean the car again, because any dust and also water will not attach into the surface of the car. So that is the application of the material. So how important the material into your life? Okay, so this is the way to block van der Waal, van der Waal force. So repel van der Waal force. Okay, so here hydrogen bonding, due to the hydrogen molecule. So it was a type of bonding, ionic bonding, van der Waal, metallic, and so on. So we have here. Okay, so I think no need here. We can escape. We can continue to another slide. Yeah. Is there any question? Maybe we need for 5 minutes. So if you want to go to the restroom, it's up to you. So afterward, we will continue to another discussions. Okay, see you. 5 minutes to go.
All right, sir.
Okay, we'll continue the discussions. Now we will focus on the content of semiconductor in our study scope.
Science out loud. Here I have a circuit with a battery, light bulb, and gap. If I fill this gap with a metal, the light comes on. If I fill this gap with glass, the light stays off. You probably already know this because metal is an electric conductor and glass is an insulator. But what happens when I fill this gap with a silicon wafer? The light stays off, so you might think the silicon's an insulator. But what if I heat it up? Thank you. It lights up. The silicon is insulating at room temperature but conducts electricity when it's very hot. It's a semiconductor whose conductivity changes based on the environment. This special ability makes semiconductors the perfect brains for electronic devices. Circuits of small semiconductor switches, called transistors, are at the heart of computer chips and enable them to do math and run programs. Semiconductors have enabled electronics to become smaller, faster, and more reliable. But what is it exactly about these semiconductors that allow them to either conduct or insulate? In a single atom, electrons can occupy specific energy levels. When multiple atoms bond, the electrons are shared between them. But because the atoms are now interacting, the energy levels shift around. In a solid, trillions and trillions of atoms interact with each other. Their individual energy levels smear into energy bands. For a material to conduct, the electrons must be able to jump from lower energy states to higher ones. The spacing of these energy levels and how they're filled with electrons determines if the material is a conductor, insulator, or semiconductor. If there's a huge gap between the lower energy levels and the higher ones, it's hard for electrons to jump to the higher ones, so current can't flow, and it's an insulator like this glass. Metals have no gap at all. Electrons can move to the higher energy levels with no problem. Current can flow. Semiconductors fall somewhere in the middle. They have a medium-sized band gap. So technically, I can make this glass conduct electricity if I added enough energy through heat to push the electrons into a higher band. But that amount of heat would either melt or break the glass before it actually conducts. This is true of most insulators. The amount of energy needed to make them conduct is just too high. But in a semiconductor, the band gap is small enough that electrons can jump into the higher energy band so that current can flow. The amount of heat we apply determines how many electrons jump into the higher band and how much current flows. And heat isn't the only way to change the conductivity in a semiconductor. We can also use light, electric currents, and in a computer, electric fields. As I've said, computers are made up of semiconductor switches called transistors that switch between conducting and insulating. Computers use electric fields because heat is slow and would burn too much energy. We can turn this wafer into a computer chip by printing a circuit of transistors on it using a process called photolithography. Here, in the photo room, we cover the wafer with a light-sensitive material and expose it to light that we shine through a patterned mask. Then, we develop the wafer, like film and photography, which leaves behind a pattern that becomes the circuit. Printing the transistors at once lets you make circuits that are smaller and cheaper than if you built them from individual parts. Transistors make up the logic elements, the memory components, and the communication modules that let computers talk to each other. With semiconductors, you can cheaply add transistors to almost any device you can think of, from spaceships to servers to maybe even your toaster. Semiconductors have enabled the technological revolution, the internet, the computer, and the cell phone. No semiconductors, no information age. I'm Jamie, and thanks for watching this episode of Science Out.
Okay, thank you. Okay. So what can you conclude from the video you watch?
May I,
May
sir?
I, sir?
Okay, please. Okay, yeah.
All right. So what I get from the video is there is in conductor which is metal and insulator which is glass, and then there is another that it is semiconductor. Semiconductor is it can be somehow it can be a conductor when that it was the conductivity change based on its environment. So the semiconductor can be used in electronic devices. For example, the circuit, or we can call it as transistors. And maybe
Okay.
that's all, sir.
Yeah. So this is our activity in the laboratory in the Singapore. I'm going to Singapore and I perform some experiment in the semiconductor. This is the example of solar cell in Nanyang Technology University, Singapore. Look at this, the laboratory, clean laboratory. Look at this, applying dry cabinet. Okay. And here, technology we apply. This is a furnace. Here is furnace. Yeah, we use in the lab. Yeah, this furnace. Here also the example of semiconductor. Okay, so this is the equipment to test the semiconductor. That's me. Axis. Okay. I like the people in the video, right? So we do the same thing. Yeah, we perform it in the lab. Yeah, if you are interested in working in the lab, yeah, so this you can join join in my lab. So this environment, are you interested? Going to overseas the world class university. Look at. Wow, it's me. Another picture I can share with you. Here. This way. So this is solar cell, handmade solar cell in the lab. This one, solar cell. Yeah, can convert light energy into electricity. Look at it, the solar cell. This is the material for the solar cell. Molybdenum. Yeah, here. Okay, this one. Here, the solar cell made of rice, black rice. This one, solar cell. This we are working at the lab. Wow, it's me. We copy it in IPS, yeah. Okay, so this is a real lab. Yeah, you can imagine how the lab look like. That's the real laboratory. Yeah, in the university, Wood Class University, School of Electrical and Electronic Engineering. Wah, teknik elektro ya. Another documentation I have here. This is in Japan. I can share you. So wait a while. Oh, sorry. We are waiting. Wow, this is what is it? It's a lab in Japan. Yeah, so this also the equipment. It's very different from the lab in IPSC, right? It's a real lab. It's a real laboratory. Yeah, you can see. This me, yeah, our student ID. This a lab. Look at it's an equipment to make a battery. Because here in the environment is argon. This to check the solar cell. This to check material. Yeah, here. This is we have also in my lab. I have this equipment in our lab in UPI. Yeah, I have the equipment. This is here solar cell flexible. Another thing you can share here is the unique. We can see here. Where is it? Open. How to open? Oh, here. Look at very clean water in Japan. Look at the water is very clean. Yeah, there is no trash. Look at another here. Look at the color is greenish and yellow. Do you want to go? Yeah, you have a dream to go. Wow, that's the color. Okay. Another experience you can see here. Here. This is in the campus. Wow, everything's red. Yeah, okay. The leaf is red. Yeah, this a campus environment. This is in the normal situation without COVID, but look at nobody working. empty campus. But it was in the reality. You will feel alone over there. Okay. And here our laboratory. Yeah, this is my lab. I can share. This is my lab. What we are working at the laboratory. Working with material. Here. In UPI. This in UPI. Sorry. This is our lab in UPI. Yeah, working on material. Wow, this is in Jika. This is our lab. Yeah, so still simple, but it worked. It worked. That's material. Synthesis of the material. It's a solar cell. Yeah, in the lab. So we will do this experience with you in this course, inshallah. Yeah. There's a material having a different color. Look at. It's interesting. Yeah, from organic compound. Okay, another example. This is we perform the experiment. Yeah, campur-campur ya. So, do you think I'm chemist or physics? Yeah, I combine it. Chemistry and physics merge as science. Okay. Yeah, this is what can I share to you in our real life. Okay, as scientists. Any questions? Before we continue.
I have questions, sir.
Okay, Vicky, please. Okay, please.
I have two questions. So the first question is, as we know, as Sir saw before, that the unit cell is composed of the 4 atom lining in one structure. That's the unit cell. And then there is the limit. It's called grain, right, sir?
Yeah.
And then
yeah.
we said before the memory card that we use right now, for example, the 64 gigabytes. The thing is, the differences about the 32, the 64, or the 8, but the card is the same.
The card is the same.
Card is the same. The difference is that it's the grain of the atom.
Yeah,
Yes.
the grain.
And my question is there any limitation that the scientists can found in the grain, like the smallest, like the scientists will say, I think this is the smallest part of the grain that we cannot further do, cut it or make it like this is the last. This is the last grain.
Yeah. So there are many kind the way to what synthesis the material. There are physical synthesis or chemical synthesis. Yeah. For physical synthesis, we call it as lithography. Lithography is a process to put atom per atom. Yeah. The equipment is here. Multi-beam epitaxy methods. Yeah, lithography. You can search. We call it lithography. It will be easy to control. The name is Sorry, this our recording. Here. Lithography. Here, lithography. So lithography is the process to put atom by atom physically. Here, electron beam lithography. So that by this physical synthesis, it will be easy to control the formation of the grain.
This short video will teach you the basics of electron beam lithography. Lithography is a word that comes from ancient Greek, meaning printing with stones. With this technique, a stamp is made by carving a pattern into a stone. The stone is then coated in ink and pressed onto a substrate, such as paper. Similar methods are used when making small microscale devices, where a pattern needs to be made repeatedly on wafers. The two methods used are called electron beam lithography and photolithography. EBL uses electrons to print, while photolithography uses light. Both methods use an organic material called a resist, which is sensitive either to electrons or light depending on the material used. A thin coat of this resist is applied to the substrate. In photolithography, the resist is exposed to light through a patterned mask that has been transferred onto the substrate. Wherever the mask allows light to reach the resist, a chemical reaction occurs, in which large resist molecules are broken down into smaller molecules. After exposure, the next step is called developing. The area of the resist that has been exposed to light is removed by immersing the wafer in an organic solvent. The solvent dissolves only the small molecules that were produced during the exposure to light. Finally, the pattern is transferred onto the substrate using one of two available methods.
Yeah, so here we'll represent a grain decay. Yeah, using a photolithography physically.
Method 1 is etching, in which substrate is chemically removed from the pattern area that is not coated in resist. After etching, the remaining resist is removed, revealing the pattern etched into the substrate surface. Method 2 is the lift-off technique, in which a metal layer is deposited over the whole of the wafer. The resist is then removed, taking the metal layer with it. The only area that now has a metal coating is the desired pattern, where the resist had previously been removed in the developing step. Electron beam lithography uses the same process scheme, but a focused electron beam is used for exposure. The beam is accurately directed to positions on the wafer to form the pattern. The electron beam exposes the pattern.
Yeah, as remember, it's only light who are able to take care the material in nano size. Do you remember? Yeah. So our hand is not us, but using light. Yeah. Okay.
Dot by dot and line by line, which can be more time-consuming than photolithography. However, it is a more flexible system and does not require expensive masks. The focused electron beam also allows feature sizes below 10 nanometers to be generated. Common applications for EBL are rapid prototyping, small batch production, where electron beam lithography and photolithography are used in conjunction, as well as the fabrication of masks and imprint templates.
But now you can study how to make a Intel processor. Look at this, how CPU is made.
You are about to experience a fascinating journey through the clean rooms of the semiconductor industry. See integrated circuits in the making at one of GlobalFoundries chip factories. Let our experts walk you through the nanocosmos of the atom.
I can apply a job into Intel, yeah, due to my expertise.
A world that normally remains hidden from our eyes. In the beginning is the circuit diagram. At design centers around the globe, experts collaborate to design circuit diagrams, sophisticated integrated circuits like microprocessors, high graphic processors, and wireless communications ICs. The next step is manufacturing. The disk substrates for the microchips are made from quartz sand and are called silicon wafers. To make these wafers, a huge monocrystal is drawn from purified silicon melt. The result is a perfect silicon lattice into which the transistors will later be fitted. However, impurities pose a threat to these flawless silicon crystals. Our GlobalFoundries manufacturers must therefore take extensive precautions every time they enter our dust-free clean rooms. The result? Our wafers are fabricated in an environment that is more than 100,000 times cleaner than an operating theater. Completely free of dust, the silicon discs arrive at the clean room. Here, 25 wafers are packed into each hermetically sealed container and sent off on a journey that will take them through hundreds of manufacturing steps.
200 manufacturing step. So we will end the class at 7:30, yeah. Okay.
Photolithographic techniques transfer the circuit structures to the wafers, rather like slide projection. The key to this whole process is a solid mastery of light. The The silicon disc is spin-coated with a photosensitive resist. UV light transfers the circuit structures depicted on a mask to the wafer. The exposed parts of the resist are soluble and are removed by a developer. The transferred structures can now be used as a template. The unprotected parts of the water surface are etched away. The structures of billions of small current switches are generated on each wafer, tiny transistors. From the photolithographic stage, wafers move on to the ion implantation, where the electrical properties of the transistors will be specified. Here, the engineers make good use of one of silicon's most important properties. Silicon is a semiconductor, which means that its conductivity can change via a high precision emplacement of so-called dopant atoms. First, dopant atoms are injected into the silicon structures. These atoms then distribute randomly in the silicon lattice. At high temperatures, the doping atoms become flexible and take on a fixed position in the atomic structure. The complexity of manufacturing tiny transistors requires a clean room as big as 2 soccer pitches. While our people monitor the complex process.
Yeah, so what can I conclude? Inside Intel processor, there are lots of process manufacturing to be completed so that the atom could be placed in what we expect. There are doping, etching, and then firing, photolithography. Okay, so many things. Wow, it's wonderful, right? Okay, maybe we still have a time next week, to continue our discussions regarding semiconductor, and then continue to another discussion about thin film technology. Okay, so are you interested? Semangat. That's a new modern era of modern physics. So we relate it into a real life, into the new thing you have listened now. Okay, is there any questions? So I have provided assignment. Maybe some part of the material have been discussed today, but another part of the material you have to read it from what I have uploaded to Spada. Maybe you can easy to read, and then my question is to derive our goal of today's meeting. Okay, any questions? We will meet next week for another topic. Okay, so thank you for the lesson today. Thank you for your interested in our topic. Maybe you can enjoy us and you will get a real experience. I expect you can go to our laboratory. That's very special. It's only you selected to come to our lab. It is my lab. Okay, thank you. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you very much, sir.
Yeah.
Thank you, sir.
Yeah.